Overview of electric vehicle technology. There are four technologies: motor drive technologies, resource technology, vehicle to grid battery charging technologies. Here we'll discuss the vehicle to grid technology and battery charging technologies. The vehicle to grid technology in an integrated smart system, the electric vehicle with vehicle to grid is capable to send power to the electric grid. Is nothing but the vehicle to grid technology. With the vehicle to grid technology, the car would supply electricity to the grid. An automobile with vehicle to grid is referred as mobile energy or smart charging. So vehicle to grid is the technology where the system can send back energy to the grid, and also it can be charged from the grid. The main benefits of this V2G technology are profitable grid management, called as the ancillary services. That is the other than power also it can provide support to the grid for management purpose. Ancillary services support to stable operation of the system. Also, it can support grid frequency and voltage to maintain it steady. The integration of electric vehicles in electrical power systems provides some challenges on technical, economic, policy, and regulatory issues that can be managed with new architecture concepts and algorithms and procedures with vehicle to grid technologies. Plug-in electric EVs offer an uncommon opportunity to address energy security, air quality, climate change, and economic growth. The market growth is uncertain due to the policy, economics, and technical challenges, and easy adoption of plug-in electrical vehicle nationwide. Some recommendation to promote adoption of EVs are regulatory framework for innovation to increase the PV value without compromising the reliable operation of the electric grid. Public and private investments in charging infrastructure. Facilitate PV rolls out for easy purchase. Consumer education on PV technology. So the plug-in electrical vehicle have these few recommendations for their adoption. A smart grid with plug-in electrical vehicle, plug-in hybrid electrical vehicle is shown here. So the vehicle can be observed that the vehicle can be the part of the grid. So it can receive the energy or it can transfer the energy from the vehicle battery. Also, other energy sources are the part of the grid, that is renewable generation, wind generation, solar PV. Houses are connected with the renewable. So there are consumers who are producing the electricity, and also vehicles are there which have the plug-in capacity or plug-in hybrid vehicles. The plug-in is the bidirectional V2G, and they charge the grid, and these are the distributed storage systems. Energy supply to the grid is priced that pays back the additional cost of V2G batteries. The distributed storage will be like make the grid more stable, secure, and resilient by frequency regulation and spinning reserve as backup capacity with distribution system. Vehicle to grid system allows greater penetration of renewable sources such as wind and solar into the grid. V2G promises prominent application in the global transition to the emerging green and sustainable energy economy. A large-scale penetration of plug-in electrical vehicles will impact different aspects of the power grid system. power grid. The average operating temperature of the transformer will increase under the additional load of charging of the plug-in electrical vehicles. This will shorten the life, thus adding cost to the electric grid. There will be potential power supply shortage if aggregated battery charging profile includes the on peak period. So during the peak period, if the charging is increased when the plug-in electrical vehicles are connected, so it may provide the shortage of supply. The battery should be storing electricity from the lowest carbon emitting sources, or maybe from the renewable energy, maybe from nuclear. But the challenge is to make the two demand and supply load curves coincide. So the additional challenges are there when we go for the plug-in hybrid electric vehicles. Another is the battery charging technologies. For electric vehicle batteries, there are following common charging methods. First is the constant voltage method. In this, the battery is charged at constant voltage. This method is suitable for all kind of batteries and probably the simplest charging scheme. The battery charging current varies along the charging process, keeping the voltage constant. The charging current can be large at the initial stage and gradually decrease to zero when the battery is full of charge. The drawback of this method is the requirement of very high power in the early stage of the charging at the initial stage, which is not available for most residential and parking structures. Second is the constant voltage. In this, the charging voltage applied to the battery is controlled to maintain a constant current to the battery. The SOC increases linearly versus the time for a constant current method. The challenge of this method is how to determine the completeness of the charge with SOC 100%. The cutoff can be determined by the combination of temperature rise, temperature gradient, voltage increase, minus voltage charge, and charging time. The combination of constant voltage and constant current methods also is the third type. During the charging process of a battery, normally both the methods are used. At initial stage, the battery can be pre-charged at low constant current if the cell is pre-charged before. Then it is switched to charge the battery with constant current at higher value. When the battery SOC reaches a certain threshold point, the charging is changed to constant voltage charge. Constant voltage charge can be used to maintain the battery voltage if DC charging supply is available. The graph shows initially it has a pre-charge, then constant current method is applied. You can see the change in the voltage. Now, during the next period, constant voltage is there. So you can see the voltage is constant. So after the charge is complete using this constant current charge and constant voltage charge. There are few standards related to the electric vehicle charging. So National Electric Code 625 vehicle charging system gives the standard for vehicle charging systems. The CEJ 2293 gives energy transfer system for electric vehicle standards. Next, SEJ 2836 gives recommended practice for communication between plug-in vehicle and utility. SEJ 1772 gives electric vehicle conductive charge coupler standards. Another standard SAE J1773 gives electric vehicle inductively coupled charging standards. Also, IEC 62196 gives plugs, sockets, outlet, vehicle couplers, vehicle inlets, conductive charging of electrical vehicle standards. And IEEE 1547.3 gives interconnecting distributed resources with electric power systems because these plug-in hybrid sources are the distributed energy sources kind of system. If you see the charging levels as per the industry standard SAE J1772, there are three charge levels. The level 1 uses the US standard 120 volt AC, 15 ampere or 20 ampere branch circuit used in the residential and commercial buildings. It delivers 1.44 kilowatt maximum power, and this method requires a dedicated circuit for the user to avoid overload. This is the simple and most immediate solution. In level 2 is based on 240 volt AC single phase with 40 ampere current, requires a dedicated circuit. Under 15 ampere, the maximum charge power would be 3.3 kilowatt. This method can be implemented for both residential and public charging. Third one is the level 3 is the method suitable for fast charging through public facilities or public charging stations based on 480 volt AC three-phase circuit with 60 to 150 kilowatt charging power. This option provides number of specific safety precautions. Level 3 charging may recharge the battery up to 80% of capacity with a short time. Battery charging technologies can be conductive type or inductive type. Conductive means connecting the charger simply into the plug by physical wires. And inductive mainly include the wireless power transfer, that is WPT, for battery charging. To facilitate, there will be far field method technology and near field. In the far field wireless power transfer, it uses microwave radiation or laser to transfer high power over long distance. However, it requires complicated tracking strategies and large antennas, which are impractical for EV applications. So the near field wireless power transfer makes use of electric field or magnetic field for short range to mid-range power transfer. By using an electric field, the capacitive power transfer technology takes the advantage that the power transfer is unaffected by metal barriers and causes low electromagnetic interference. So CPT, that is a conductive power transfer, can be used. The magnetic field wireless power transfer technologies have been identified to be the most viable for electric vehicle battery charging systems. The principle of inductive power transfer for electric vehicle battery charging is based on the magnetic coupling between two coils of a high frequency transformer. The high frequency is to transmit power without more losses. One of the coils is installed in the charge coupler while other is embedded in the vehicle. So one coil is on the charge coupler point and another is into the vehicle connected to the battery. The main AC supply with frequency of 50 or 60 Hz is rectified and converted to high frequency AC power of about 80 kilohertz within the charger module. Then the high frequency AC power is transferred to the plug-in hybrid electric vehicle or pure electric vehicle by induction. And finally, this high frequency AC power is converted into DC power for battery charging. The IPT can operate over wide frequency range and can readily be scaled up to meet various power levels. The corresponding core losses and electromagnetic interference are our main concern. For instance, a well-known but obsolete IPT-based EV chargers, magnet charge, deliver 6.6 kV at an efficiency of 86%. So the figure shows the IPT technology where supply is taken, it is rectified, converted into high frequency using the inverter and given to the charge coupler at one end. At the vehicle inlet, there is another coil connected to the rectifier which receives the energy with high frequency with this another coil, again rectified and suitably converted to the DC level by using DC to DC converter and given to the battery. The park and charge facility is there in order to facilitate the charging of the EV. The magnetic field of wireless power transfer technology is extended to be plugless. There is no any wire, which is the primary coil installed on the floor of the garage or in the parking lot, and secondary coil is into the vehicle. So when vehicle is parked, it will charge wirelessly. The system is very easy to use and the charging process takes place automatically once the driver parks the electric vehicle correctly in the vicinity of the coil. This plugless park and charge not only increases user convenience but also offers means of overcoming the standardization of charging. The existence of large air gap or clearance between the primary and secondary coils, IPT technology is less suitable losses and reduced power transfer. EV move and charge type of charging, that is a MAC. Rather than stopping the vehicle at parking, electric vehicles are charged during moving. As shown in the diagram, an array of power transmitters are embedded beneath the roadways or the zones, and this number of coils are there on the road, called as a charging zone or lane. And the receiver is mounted into the bottom of the electrical vehicle, as shown here, and it will receive the energy while moving, that is the wirelessly. The move and charge technology solve the long-term problem of pure electric vehicles. The high initial cost and short driving rates. The problem is solved by this. PEV can conveniently charge at the charging zone during the driving, hence automatically extending the driving range. The technical problems or application of move and charge are efficiently WPT depends on the distance between the transmitter of the array and the receiver of the vehicle. And the distance is time varying and affected by the road condition and the vehicle payload. The resonant frequency of the WPT is not constant. So there will be change in the power transfer. Effectiveness of MAC operation heavily depends on the coverage of WPT as well as the position and speed of the vehicle, which is running in the zone. The location of power transmitter need to be optimized in such a way that the electromagnetic field intensity at different locations over the charging zones should be uniform. And the MAC operation needs to distinguish which EVs are authorized to retrieve the wireless power or to prevent unauthorized access to the energy.